All right, so we did chapter 9 and 10 a little bit in the previous video. So I'm going to be mostly focusing on chapter 11 here. So we have a figure skater that can increase her spin rotation from an initial rate of 1.1 revolutions. So let's draw this. The person, we'll just ask her this first. If her initial moment of inertia was something, what's her final moment, and how does she physically accomplish this change? Remember that inertia is like how hard it is to turn something around an axis, sort of. And here you would imagine it as she's got her arms out versus she pulls them in and hugs herself, kind of. So that would change her moment of inertia, right? Because she has less radius exiting out from the center, and there's like less torque on the ends of her hands. So at the beginning, she's got her arms extended like that. I'm just gonna do a little triangle here. She's churning. And then at the end, she's got her arms like crossed over. She's still churning. But faster. That's the faster. So then let's put momentum. No, sorry, not momentum. Inertia. So here, oh, not red. Leave a space for the knot. What is it, 4.6? Yeah. Kilograms, meters, it's squared. I'll put it. We have I final is an unknown. That's what we're solving for. And we have revolution of 1 per 1.5. And then here is revolution goes 2.5 revolutions per 1 second. Right? So this just says 2.5 revolutions per second. So you're assuming that's a 1 second. So then if you remember, frequency is revolutions per second, right? So then we can convert this into frequencies. Oh, no. So let's see. Equals 1 over 1.5 is about 0.67. I'll just put F equals frequency. No, it's not really spaceful. And we have, oh right, I need to leave space for the knot. That's annoying. Yeah. And this one's just 0.5 because over 1 second is the same thing. Revolutions per second. Cool. So then we can relate that to the omega. Because if I remember correctly, frequency, oh, that's a badass. Frequency is equal to 2 pi, no, yeah, omega over 2 pi. So omega, I'll do this one in a different color, in black. Omega is equal to frequency times, I guess it'll be 2 pi frequency. Just so you know that you're multiplying the two. Make sure that looks like a 2. There we go. So then you have moment of inertia. No, not a moment of inertia. Angular momentum. Here, angular momentum is conserved. So I'm gonna use W. You just know it's an omega. I'm not gonna use W. My omega. Five, not, oh, not black. It's I omega. So then we know that, oh, I can just get from there. If we divide this omega over, it cancels this one out. And we can solve for I, which is what we're solving for, right? Is there a question mark over there? So then you have initial moment of inertia times initial rotation, angular velocity over new angular velocity. And then from there, you plug in the omega equation that we made or remembered. This one. So then I initial times 2 pi f naught, right? Because this one's f naught, this one's f initial, f final, over 2 pi f. We can cancel out the 2 pi's because they're division. And then that gives you I naught frequency naught over new frequency equals the new moment of inertia. Sorry, new inertia, not moment. Yeah. Sorry, I'm a little tired. Anyway, from there you plug in I naught was, as we saw, 4.6 kilograms meters squared. The frequency of the inertial is 0.67 revolutions per second. And then you have the new one, which is 0.5 per second. Note that these units cancel out. So then that gives you meters, kilograms meters squared, which is what you expect for inertia. So then that gives you I is equal to if you plug that in, it should get you 1.23 kilograms per meter squared. then that's your answer. And then how does she physically accomplish this? She pulls her arms in. Cool. There it is. I think this one was just, sorry, to show you that like when you pull your arms in, because this was from the class, right? You have angular momentum is conserved in that case. So then this is constant. And that's what we showed here. Like if you equal this to each other, you get your mu moment of inertia. And here, when she pulls in her arms, the angular velocity increases, but the moment of inertia decreases because the momentum stayed the same. So they needed to change. So that's what this was showing me. Now, I know we do cross product in this one. I kind of suck at cross product. So here's some stuff that I found. I remember using this IJK method a lot. Or for me, it looks like this. You do I, J, lowercase, J, K. And then if you're moving like this direction, then it's positive. But if you move the opposite direction, then it's negative. So here you see right here. If you go across I with J, so let me do this. I with J, let's do a different color. I with J gives you K. That's this one right here, right? Then if you do, but if you do J with I, it gives you K, or negative K. Yeah, because then this one would be going this way. So J with I gives you negative K, which is what this one shows you here. And then just if you cross the same one with the same one, it's equal to 0. And then there's a little explanation over here of why, because like if you go I to J, then it's like 90 degrees, right? That's 1. But if you go like I to I, then it's 0. Versus with like dot product, use cosine instead of sine. So yeah. And then this is like a matrix version that people use. I never really learned that. So cross product use sine. Wow. Dot product uses cosine. And then remember that cross product results in a vector. While dot product results in scalar. So a vector has like direction and velocity. Sorry. Direction and magnitude, whereas like a scalar only has magnitude. So scalar would be like work. Cross product would be like, I believe here we're using it for torque, right? Something like that. Yeah, for torque. Anyway. Oh no, not the text. And I can't change it anymore, can I? Oh well. Anyway, this is another version. I think it's called the matrix. So for C1, you do like you cross it this way. No, cross that way, and that way. And then for C2, cross these two. And for C3, cross these two. So it's like whichever ones you can hit by a diagonal, I think. But either way, you're always kind of like gonna cross a different one. So that's that one. And then this one's kind of going backwards. And then this one's going like this. I definitely recommend looking at videos because I know I'm not doing a good job of this. And then this is Dr. C's answer. She just says the determinant formula and gives you this. And then I guess you plug those in based on what you got here. And then that's your answer. I tried doing it the way that I remembered, but it came out wrong. So I don't really want to teach you guys that. Because basically I used to just it sound very elementary, but foil this out like that for each thing. Oh, not for that. You add a 0j, and then you do like all three of those for each of them, and it gives you this really long equation. And then from there you look I cross I, that's 0, cross it out. I cross j, that j had a 0 coefficient, so that goes 0 away. The I cross k, that's going to be negative j and stuff like that. But yeah, sorry I couldn't help more with this, you guys. Anyway, on to the next problem. So this is from my exam. This one you guys actually had on, some of these I already did. This one I did on the 11/3 supplemental Zoom, and then it was on your practice paper. This one too, I did on 10/27 Zoom, and it was on your practice paper that she gave you. This one I did also on the 10/7. It's a dot product, however, so yeah. This one, you remember dot product, you just do I cross I is equal to 1, everything else is equal to 0. So you only cross those. And then the last one from my exam that I wanted to go over was this one. So let's do it. First thing, you have to note that they give you an equation. So that means you're gonna derive, like using derivatives. I guess that's calculus. So give equation, so you're using derivative / calculus. You remember here that you have, where's the draw? Where's the draw? Velocity is equal to delta x over delta time, right? So if you're turning that into angular, then velocity becomes omega and x becomes theta. So you don't actually have to remember like these equations if you don't want to. And similarly, a is equal to dv over dt, right? And that becomes alpha is equal to delta of omega over dt. And remember, I did a little chart up here in chapter 10 that like displacement, x becomes theta, v becomes omega, a becomes alpha. And then we also have some of these equations here. So we're actually going to steal one. I think we're actually going to need a few of them. I guess I'll come back when we know more about the problem. But first off, it asks for the angular velocity at a certain time. In order to get that, we have to use this derivative here, right? So we're given theta, and we're going to derive it. So theta to omega is derivative. Let me move something. Move this. Yeah. So then we're gonna go and do our little derivative. We do this 2, we take it, we put it in the front, and do -1. We think like, oh yeah, there's a t to the 0 here. We're gonna take that 0, put it to the front. So then omega becomes, I can probably type this, 2 times 2.72 radians per second squared times t to the what? It's now 1 plus 0. Right? T to the 1. And then if we're doing omega to alpha, then we're going to do that whole thing again. We're going to take this 1, multiply it down to the front, to -1. And so then that gives you 1 times 2 times 2.72 radians per second squared times it's now t to the 0, so you're not going to bother writing it. Right? And then from there, you just plug in for time. Note here that because you get no time for the alpha, it becomes just constant acceleration. And so if you multiply that 2 into the 2.7, it's probably going to give you 5.44 seconds squared. Note, no t, so constant acceleration. Cool. And then here we just inserted it, right? This becomes this. This becomes that. This is time. I guess I'll do it in a different color. This is time. I'll circle them. And then that gives you your answer there. So then C, calculate the components of linear acceleration at time and calculate A. So we've got a particle moving in a circle, right? It's moving. Ooh, I have stamp. There's a stamp shape. It's moving in a circle. I can draw a nice circle. So, right, we have both tangential. So if we're turning it into linear, we have tangential acceleration. And we also have centripetal acceleration. So right, because both of these are linear. Cool. So Then we need to find the equation for these. And we will do that right now. It was this one. It's a little hard to see, but centripetal acceleration is equal to A omega t. If I can copy and paste that into annotations. Let's see. I cannot copy and paste. Fun. Okay. Good draw. So this one says what? Tangential? Yeah. So equals R alpha. And then centripetal is omega squared R. Cool. I'm gonna go back to the problem. I think you could also derive the centripetal if you knew that a radial is v squared over r, and then v is equal to r omega, but either way, you're gonna have to memorize all of these, so. Yeah. So then you have, I think radius was given. Yeah, radius was given earlier. So this is r. And then you found omega, or sorry, alpha and omega. So then you use both those. So then you plug in. And you plug it in previous answers, and you get a tangent is equal to 5.44. Note that you can plug these in because you use the same time. I mean, for the tangential, you're using alpha, so it's not going to really matter. But for the centripetal, because you're using velocity, it does kind of matter that you have the same time. Omega we found as 2.45. So add another 5. Right. Then if you plug that in, equals, let's plug that in. I think that should be 13.6 meters over second squared. And then for centripetal acceleration, that should be 2.45 squared. 5, about 15.01 meters per second squared. Right? And then you have to do the what's it called? Square root thing. Because you're gonna need to find the total. Yeah. Oh my gosh. You guys know what I mean. The Pythagorean theorem. That's what I mean. Yes. It doesn't really matter which one's X or Y because they're both on the legs. I guess I should find where we got these. Same time. Because you have the same time, that's why you can use it. And then this one there. And then from there, I'm like, all right. It kind of looks like that, right? Because you do tail to tip and gentle, centripetal. So then you do the Pythagorean theorem, and A is equal to the square root of A10 squared plus A centripetal squared. And then that gets you A is equal to A space for the square root. 13.6 meters per second squared. Squared. I guess I could write that. Plus 15.1 meters per second squared. So I could write that squared too, huh? So that's second squared. Squared. And then all of that is squared. The squared and the seconds is just for the units. The other one is for the Pythagorean theorem. And that should get you. Let me plug it in, sorry. Uh, 20.25-ish. So I guess it's 0.3 meters per second squared. Cool, and then that's your answers. I hope that helped, and I think that's it for today. Good luck, you guys.